let's go ahead and get started. You know, where we left off on Wednesday, and we really just started to dive into this topic, is that it's really going to take some just time and experience and practice with getting good at using pointers. And so I think our goal isn't necessarily, true expertise in the understanding of pointers. Our goal should be, awareness of what they are meant to be and how they are used, and a decent conceptual map of what your code then corresponds to underneath the hood. Because as it starts to get a little bit trickier, as you can do some more advanced things with pointers, if you can remember the very basic conceptual map, I think whether it doesn't make the code easier or not to figure out, at least you're not just going in blindly. And I tend to see that a lot in sort of introductory programs that are using pointers. Let's go back to just the big picture concept, right? A pointer is just a type of variable. And it's a type of variable that's meant to refer or point to an address in memory, a location in memory. To be a bit more precise, it tends to point to a location of another variable in memory. So a pointer is both a variable, and it also stores the address or the pointer of another variable here. And for that reason, although it's really a design decision in the language versus a strict requirement that one do it this way, because each of our data types we know is going to be a different size in terms of the number of bytes that each variable of an int or a char or a custom structure that you create are going to require, our pointer variables that we then declare and use in our code also have to be data type specific. And that's just the first thing that takes a little while to get used to, that a char pointer is different than an int pointer. In some sense, they're similar, that they're both storing addresses. But how we use them is going to be different because pointing to a character is got slightly different rules than pointing to an integer in terms of where these things can be located in memory. So syntactically, how we generally declare and use our pointers is just with this example here. So if we have an arbitrary variable of an arbitrary data type, and there I'm being intentionally kind of generic and I'm just calling it data type. When you see that, you can think of an int or you can think of my custom structure, and then that's the data type we always declare first, then the variable name or array of that data type. We then can separately, at any other point in our code, declare a pointer variable. It looks very similar at first blush. If this was int a on this first line here, this one would be int star a. And you can just say it like that if you want to be really explicit about it. I am declaring not an integer anymore on that second line, or a variable of that data type. I am declaring a variable that is a pointer to that data type, a pointer to either memory or to another variable that's stored in memory of that particular data type. If you've got that, you're in really good shape. And that's the primary fundamental difference between those two. I use the first example when I want to just declare an int or a struct. I use the second example when I want to declare a pointer to an int or whatever variable type or whatever struct I have there. The rest of the syntax is just as what is shown here. You can explicitly set a pointer in a couple different ways that we'll see, but one mechanism is to use that address operator, that ampersand operator, and I would read that out loud as pointer name is equal to the address of variable name. That's how I would say that out loud. So when you see ampersand in this context and not in the logical or bitwise and operators, it's not really and anymore in this context. Maybe they should have used something different, but they had limited key sets and character sets and keyboards and things like that. So pointer name is equal to the address of variable name. That is what we were doing here. We printed out some of those raw pointers on Wednesday. Part of your takeaway should be, we don't usually strictly care about the actual value of the pointer, like is this address 10,000 hex or 20,000 hex or 2 million hex? We usually don't care about that, but we need to have the mechanism to explicitly set our pointer, to initialize our pointer. And we wouldn't want to initialize it to a value of like 3 or 4 or 0, for instance. It should be, if we were to later use that pointer to access memory, be initialized to something that's pointing to a valid location in memory, a place in memory where we know there is something. Where exactly is variable name in memory? We've talked a little bit about the stack, if it's inside a function, or if it's global memory. We'll talk about dynamic versus static memory. There's a lot of implementation detail there, and I think for the most part, you can just assume it's put somewhere reasonable. The compiler, in concert with the operating system, figures out when you've declared variable name, what's a reasonable place to put variable name in memory. And now when we want to indirectly access that address in memory, we would have a pointer, we would set it to explicitly be set as that address of that variable in memory. That's kind of the first half of using a pointer. If we want to explicitly set our pointer to the address of another variable, that is one mechanism by which we can do so. The other part is using that star, the asterisk, the multiplication symbol, whatever you want to call it, in a similar kind of way. We already used it when we declare the pointer variable type. Now when we want to, and the term, as I used it on Wednesday, I see it used both ways. Is it referencing or dereferencing? To me, it would be referencing a pointer, but let's just call it following the pointer, to use a term that I think is always valid and not ambiguous. We use that same symbol again immediately before the name of the pointer variable to follow that pointer. That's our mailbox analogy, to open the mailbox or find where we are on the treasure map if we're a pirate from Wednesday, right? That is following the pointer. So whatever this address happens to be, we're going to go do whatever we need to do in memory at that location. Once I've now followed my int star pointer, what I get back out is an int, either on the left-hand side or the right-hand side of my assignment operator, or inside a function argument. So whatever happened to be this variable's location in memory, I'm going to update it with whatever would be valid C that would return a variable of that data type. So you have to remember the new declaration type, the star, that signifies the variable is a pointer. Don't think of it as an int anymore. It is an int pointer. They sound very similar, but they're two pretty different things. And the reason why sometimes we can really get stuck with that is, from a programming perspective, they're significantly different. They're ultimately just ones and zeros, right? They're just bytes in memory. The variable itself is a pointer. The pointer itself is a type of variable. The pointer itself, the key, has to be stored in a mailbox somewhere. So because we have an int data type, which is maybe a 32-bit value, we may also have a int star, a pointer data type, which may be a 32 or 64-bit value. If you're not careful, you could do int stuff with your pointers, and that may or may not be valid for your program. But for now, just know that when you see this, it's not a huge change. It's just we're declaring something to be an address. And always think address whenever you see that variable. So when we follow or dereference the pointer, we use that thing again. This is showing it on like the left-hand side of an equality operator, but it could just as easily have been over here. Basically, once you follow the pointer, and it's of type data type, you have then access to anything that needs a variable of that type, whether it be an input, whether it be setting an output, whether it be doing an equality check. Sure.
I think I could have missed what you said earlier, but in that middle part where you said the dereferencing the pointer, how different is that from assigning the variable name to some value expression?
Assigning just variable name to some value or expression. In this context, it would have the same effect. In this simple code example. In both cases, we have a variable that's located in memory. We're indirectly kind of doing it here. We're updating that variable in memory. If we had just directly done it, var name equals 7 or something, it would give you the same exact result. So if that's the only reason you're doing it, you don't really need a pointer, for that purpose. Pointer allows this way of accessing things. Well, let's talk about a couple of the workarounds that we were using with pointers. The first is when we have our function, we want to update multiple things in calling of that function. Instead of passing all these values of these variables to this function, we just pass a series of addresses to that function. That is how scanf, for example, allows us to overwrite 7 variables if we want to in a single call to that function. That's one kind of motivating reason why we had pointers. That's how we started off this topic. I think what we'll also see is this relationship between a variable name and where it's located in memory is not always going to be a static thing. It's something that's going to change over time for all sorts of reasons. We may want, if we have an array, we may want the variable to grow or shrink over time. This is this topic of a dynamic memory allocation. And for that, we need to have pointers because we're going to be changing the location of the variable, not just the value of the variable. But I think your point and your question is very well taken, and we'll show an example of that in just a moment here. To change the value of variable name, we don't need to use pointers. It's not necessary. It's just to show how one would use pointers to update that variable name in that indirect fashion. So as you mentioned, so back to functions, we can then use these pointer variables as our function arguments. And then we are overriding not the value of the pointers themselves, but the memory locations that are being pointed to, that would then correspond to multiple input variables. We can think of that as what we were calling kind of a side effect of a function call, but usually it's an intentional thing that when we call this function, it's going to change multiple things in memory at the time we are calling that function. We talked about how using global variables is kind of a code smell, right? Because you've called this function and something outside of this function wound up getting changed because it was sort of a side effect of having called that function. Not necessarily wrong. The one example we did last week did use a global variable, but it's kind of a smell that maybe you haven't really separated your concerns very well when composing your code out of these various functions. That is still really the case when we do this, but oftentimes it's very explicit intent of the programmer to now have variables in my caller function that I want to update multiple of them when I call the function, and then we can do so via this pointer mechanism here. This is a swap operation here. How does it work? Our inputs to this function are not two integers, so it's not int a and int b. And we don't have to call the variable something underscore pointer, but if you want to make it really explicit in your code, yeah, do that. Call it something pointer. So when you look at that variable later on, you remember, hey, this isn't an integer, it's an integer pointer. Not required, but it's better than calling everything, A, B, and C, or just temp. We have two inputs that are both addresses. They're both addresses that are pointing to integers in memory. If I wanted in a regular function to swap two values, we'd have to use some sort of global memory or some other array or some other kind of workaround to do that in a single function call. But here with our pointers, we are able to swap what is pointed to by A and what's pointed to by B using a very similar mechanism to how we did swaps with our little sorting code examples, right? We have a temp to store one of the values. We then overwrite that value with the other value. We kind of recall the temporary value to update the initial value that was pointed to by A here. Every time we do that, we're following those pointers. Another way to think about that in memory, I have something at address 1000 and something at address 2000. Just to have a mental model, there's some address, 1000 and 2000. This first line says, give me whatever was at address 2000, store it in temp. Overwrite what was at address 2000 with whatever was at address 1000. We followed both those pointers. Now overwrite what was at address 1000 with what we stored locally as temp. This function does not return any values itself, and as a side effect of calling it with those pointers as arguments, we've updated two values in memory via just that singular function call. This is example swap pointers, and I wanted to show kind of two versions of what one may try to do with this. So again, that swapping mechanism we've done before when we were doing our sorting code, right? Third temporary variable to hold kind of the intermediate result. B becomes A becomes temp. Winds up rotating the values or swapping the two values here. If we were to try that without pointers, and that's what that first few lines of codes here is doing. Y equals 5 and X equals 7. If we were to call a function called swap that take as input an integer A and an integer B, and hopefully you can see that is different than the version that was on that slide, well, what would happen? We can think of this in terms of scope of variables, which is a valid way to think about what would be happening here. We can also think about it in terms of the address space corresponding to each function, that stack, where the address space for the variables in main is a separate thing than the address space for the variables in this function swap. It's both the same. It's both the scope of the variables are local to where they're declared, and the memory space is separate for the variables relative to where they are declared. So if for this first example, I'm just printing them out here, I call swap where I pass X and I pass Y to that function swap, the value of X and the value of Y will get copied into integer A and integer B. Inside this function, the values of A and B will get swapped. But the values of x and y never get swapped. I've copied those values in. I do whatever I want to do with those values, and you can change your input argument. It just does not reflect anything on the output of that function. I could have printed out a and b, and it would indicate that they were in fact swapped at that point. But after I've called the function, now when I'm back in function main and I say, after swapping, this is this, and I'll comment this out just to run it separately. If we started with the values of 7 and 5, after swapping, quote unquote, x is still 7 and y is still 5. Logically, that is a swapping operation. In terms of the scope of our variables or where they're stored in memory, you can think of it either way. We swapped it inside this function. We didn't do anything with x and y. X and y were copied as inputs to that function call. We did whatever we wanted with the copied values, but the original values of x and y have not been changed at all. We always have that limitation with our function inputs. Now, why does swap pointer work? It's the same issue. We are still limited to kind of copying inputs into a function, but now what we're copying are, as our inputs, not two integers, but two integer pointers, two addresses in memory. I still couldn't, at least via this mechanism, change the pointers themselves. I would want to call that function swap pointer pointer or something. There's a way to do it, but with this mechanism, no, we're just passing an address for A, passing an address for B. I can change those addresses, but it wouldn't reflect on the change address of my caller function. But now I can follow those addresses, changing the location of memory, which is staying the same here as it is up here, because I'm passing just an address in memory, updating that address in memory, and as kind of a side effect of having called that function, and again, I'm explicitly now passing it the address of x and the address of y, after we execute that swap pointer, we get a value of x equals 5 and y equals 7. If you're okay with this example, you're in pretty good shape with regards to pointers. You have to experience it yourself. You have to try it and trial and error yourself. And as we'll see, your code will crash a lot more as you do trial and error with regards to pointers. But conceptually, that's what's happening. We just try to visualize it one final time. We showed this concept of a stack before, and I'll actually bring it up in a little bit here, or possibly on Monday. For now, I think it's sufficient to say and understand that each function has its own kind of subset of the entire memory space. So there's a part of memory allocated to main for however much space it needs. And then for all of our functions, as we call them, there's a bunch of memory allocated to each of those individual functions. You can think of it as a scoping issue, which is also the case that if I called something A in this function, it is not the same as A declared in some other function. They just happen to have the same name. They have different scopes. They're corresponding to different locations in memory. So why the regular swap doesn't work is because these variables that are stored here never get changed by this function directly. But now instead, when I pass the pointers to those pointers are still pointing back to those locations in memory, and I'm indirectly modifying what happens in memory. Again, here I'm showing addresses 0 or 4, or byte addresses are 100 or 104 or 108. Again, we usually don't need to care what was the actual address. We print them out sometimes. Again, when doing some low-level embedded work where there's particular devices in your system that are located at certain hard-coded addresses, then you do need to have kind of raw pointers that specify a particular address. But in general, we don't care where A and B are located. We just know they're located somewhere in main's memory space, and that's sufficient. And in passing the pointer and then later following those pointers, we can modify main's memory in any function that is given as input the pointers for main's memory. I wanted us to do our playing card exercise, but we'll come back to it next week. We had a version that worked reasonably well. We'll come back to it. So despite my saying, okay, you guys have got it, making pure eye contact here with the back row, and he seems pretty confident. He's nodding every so often here. But pointers are hard, so let me just go back to that, okay? And some would say, as they've designed kind of follow-on programming languages, that having access, and to use correct term, sort of raw, non-managed pointers is a pretty big flaw in the design of C and later on C++. it allows you to really cause your programs to crash with relatively small, kind of trivial type of mistakes. So for straightforward examples like the swap pointer, we're okay, or at least we can get to an okay place. You read your Xi book, you do some coding practice, you work on the lab, you'll be okay. Things can get out of control pretty quickly, and then tracking down, figuring out why your program is crashing is usually always harder than figuring out why my program's not compiling. When my program's not compiling, I've done something syntactically wrong usually. And you look to the first error, it tells you what line number the error happened on, and okay, they're not all trivial, but you know you made a mistake and you go back and try to figure that out. When you have these runtime errors, these runtime crashes, the program will not tell you where and why it crashed. It'll just say, crash. And we've seen a couple of those inadvertently and intentionally already this semester. Where you will keep your sanity always is just to remember that. And I've said it enough times, I'm going to stop saying it. A pointer variable corresponds to an address in memory. And that is true no matter how many layers deep you want to go with pointers. How many turtles you want to have on the way down here. I can very easily, and you will see programs that do that, declare a variable, declare a pointer to that variable, and potentially declare a pointer to that pointer variable. That's perfectly valid idiomatic C programming. This example's, of course, in synthetic. And again, if you want to label something underscore pointer, maybe that helps. Maybe labeling it underscore pointer maybe helps you there, but there's probably a limit to how many pointers you want to have in your program. As best I can explain it to you, let me attempt here why you'd want to have a pointer to a pointer. We'll go through a couple more concrete examples. One of our motivations for having a pointer in the first place, and just one of the motivations, is we want to have indirect access to that integer variable. I want to be able to swap those integers when I call a function. So I have a pointer to that integer to indirectly manipulate that value when I call the function, right? That was one of our motivating reasons. So for the same reason, if I want a program or a function, that allows me to manipulate addresses indirectly, I want the pointers themselves to get changed when I call this function, and what I'm going to need then is a pointer to that pointer for the same exact reason. It allows me to change the location itself to update the pointer as I call a function here. This example is called multi-pointers. It's the same as what was on that slide. We declare an integer. We declare an int pointer that is set explicitly to be the address of that integer. We then declare, and if you want to call that int star star, or it's a pointer to a pointer. So it is an int star pointer, or an int pointer pointer. That's all that second star is implying here, that it's not pointing to an integer. It looks like it is, because it looks really similar. But what it is pointing to is whatever data type is declared before that star. So it is pointing to a variable of type int star. Which is why syntactically this is still correct here. When I want to initialize an int pointer, I want to give it the address of an integer. When I want to initialize an int pointer, I need to give it the address of an int pointer. It's the mailbox, or it's the key within a mailbox that opens up another mailbox. That was the best analogy I could come up with, or it's a treasure map that leads to another treasure map, I guess, and then you follow that second treasure map. This is not me trying to be mean with this example. For the same reason we want to have functions that will update integers, we will very often want to have functions that update pointers. So you will have int star star in your code when you want to modify that pointer. Consequently, there's a few different ways we can then call our scanf to update values here. And if this makes sense to you, you're really good. So let's go a little bit slower. Scanf, as we've been using it when I want to update an integer, I explicitly pass it an address, right? We've been doing that since like the first week of the semester. Scanf, %d, ampersand my int. Because when I do ampersand my int or address of my int, that's what I'm generating, the address of where that's located in memory. But if I already have a pointer to that location, I can just pass in that pointer. And you may look at this and say, well, that's wrong. There's no ampersand operator there because there doesn't need to be anymore. Scanf is expecting an address to correspond to that integer. That's exactly what my int pointer is. So I can just explicitly pass my int pointer, and that'll be perfectly fine for scanf. That should work just fine. Similarly, if I have a pointer to a pointer, I can first follow that first layer of pointer and that is going to be appropriate pointer to an integer. That is going to be an appropriate address of an integer. So this syntax is also perfectly valid and correct. That scanf is expecting an address, a pointer to an integer, if it's %d for our format string specifier, right? When I follow that pointer, the end result is a pointer to an integer. It's an address of an integer in memory. When I enter in 3 integers, 5, 6, 7, that's 3 consecutive scanf calls. Printing f each time is just going to print out the original my integer. Again, it's a variable, it's a location in memory, right? Whatever it is, we don't care. It's location 1000 in memory, whatever helps you conceptualize and visualize what's happening. That first scanf, we see that we've used it all semester. It's overriding location 1000 in memory. What location in memory is that scanf overriding? If the first one was overriding location 1000 in memory, what location in memory is this one overriding? Also 1000, because we just explicitly set up our pointer to also point to the same thing. This pointer is pointing to the pointer, so when we follow that pointer, the end resulting location is what? Also 1000. Okay, if you got that, you're in really good shape. I type in 5, 6, 7 for my 3 integers, and no matter what, it returns back that my int was 5, my int was 6, and my int was 7. I think that's hard. If you've all got that, that's great, as well. But that's the reason we have these multiple pointers here. Also, and I want us to spend a little bit of time and make sure we understand this. We'll be using this a decent amount. Our array variables, of course, also correspond to not just a single value in memory, but the sequential set of addresses in memory. So I have an array variable int x of 10, and it's not a single integer, it's 10 of those integers. It's not 4 bytes, it's 40 bytes in memory. That is by spec. They're not going to be bouncing all around the place in memory. They're going to be in sequential locations in memory. In terms of using our kind of pointer syntax, the address, and this is not valid C, this is just meant to kind of visualize what's happening with it, with a C-like syntax. The address of location I, offset I into array X, is equal to the address of the previous element plus however many bytes each element is, size of int or size of whatever that data type is. That's always going to be the case when we declare an array, at least for the virtual memory that the operating system provides to us as a programmer. The values for that array are going to be in sequential locations in memory. More importantly for our discussion of pointers this week, the empty array name syntax, where I just use X in my program versus X of something, is not actually essentially, is literally a pointer to the first element of that array. That is just part of the C specification. We've been kind of using it without realizing it all semester, but now we can look back at our scanfs and understand what is happening here. It's literally a pointer to the first element of the array. If I've declared an array called int x of 100 in my program, and later on I just use the value x, not x of something, just x, that is the same, that is syntactically the same, that gives me the same exact result of address of the first element or address of x of 0. You can use address x of 0, but you don't have to use address x of 0. If you just use x in your program, that is literally a pointer. It stores the address of where that x array starts. That is why when we did scanf on a string, we didn't have to use the ampersand operator. We could have, but we were passing it in an array when we want to type in your first name, right? And we had a car first name of 50 or something. We would just pass in first name as an input to scanf in that case, and not needing the ampersand operator there, because the name of that array variable, first name, last name, whatever it may be, is literally a pointer. It stores the address of the first element in that array. That's what allows us to pass these arrays as inputs to our functions without having to explicitly kind of copy all those values along. We talk about arrays as being that other kind of workaround for having one function call update multiple things in one call. It's really not a separate workaround from using pointers. When I pass arrays to my functions, I'm passing pointers to the first element of each of those arrays. It's the same as explicitly passing pointers to those functions. Unless it's a C string, you're still responsible for keeping track of the length of the array yourself. So there's an equivalency here. This is a kind of code we looked at a little bit earlier when we were just talking about arrays in the first place. I want to do a dot product of two arrays. Array of doubles called A, array of doubles called B, a separate variable to keep track of how long each array in terms of valid things are. We get our for loop, we do our C plus equals A of I times B of I. Name of the array is literally a pointer to the first element in that array. The converse is also effectively true. Can be in this instance. Not all pointers can point to arrays, but all arrays have pointers. So you can write an equivalent version of this code that doesn't use the array syntax for our variable inputs at all, and instead just uses pointer syntax. So this version of the code is equivalent. Some quibbles about how compilers treat pointers versus array syntax and whether there's some very slight changes in the code that gets emitted, but conceptually, from a functional correctness perspective, the codes are equivalent. Go back to it quickly. This one is how we've been doing it. We pass arrays. This version is equivalent. As long as we have correspondingly passed the same array inputs to it, if we have a pointer, we can take the offset of an array, assuming that that pointer is pointing to an array. So that every time we have that pointer syntax, we can use the array syntax instead. We got a few minutes. We're good, we're good. Most of us are good. You generally should only use that array syntax if you have an array. You're allowed to use that array syntax throughout. If instead of my int and printing that out like we have been, and we did the version we could follow my int pointer. That is still valid syntax. That'll print out the same, I guess it would print out the final value of 7 here. We can also use the array syntax for it. Follow that pointer and give me the first element that is pointed to from the beginning of that pointer. I'm showing you that syntactically, from a correctness perspective, this does work. Usually you still only want to use the array syntax if what you're pointing to is an array. Because while this technically works, I have no idea what that would do. So that's a bug, and it's a pretty subtle bug, right? I just changed that one value, and it's hard to say in looking at the code, was this a valid bug or not? It would point to whatever's next in memory after that integer. It depends on implementation. I don't know what's next in memory after that integer. Some arbitrary location, some arbitrary value in memory when we offset it by too much. But just to convince you that that array syntax is equivalent, when I do offset of 0 again now, fingers crossed, we get 5, 6, 7, and then it does print 7 back out again afterwards. So all arrays have pointers, but not all pointers necessarily point to array. But in general, x of I is the same as follow that pointer with an offset of I. And syntactically, you could do that as well. Instead of my int pointer of 0, we're basically saying follow my int pointer with an offset of 0. That will also give you the same exact result. So similarly, this code could also be implemented without using that array syntax at all. You can just access the pointers indirectly, follow the pointers. Again, I think a good rule of thumb is if your concept is involving pointers, if there are pointers, or excuse me, if it involves arrays, if there are arrays declared, if you're dealing with arrays of data, then use the array syntax. If you're just modifying locations in memory, then just use the pointer syntax. But there's an equivalence to it. You can continue to use that empty bracket syntax for pointers to multi-dimensional arrays. It just starts to get a little bit messy, and you start to see it less and less code. So x of this is a pointer to an array of arrays of size 3. So the innermost dimensions have to all be defined of a fixed size, but the outermost dimension can just be a pointer. Y of bracket for 3 is a pointer to an array of arrays of size 4 of arrays of size 3. You can do that in your code. I think as you start to get multi-dimensional data, beyond one dimension, so we're talking 2, 3, or beyond dimensional data, This is just my observation that just more conventional pointer syntax is more common for accessing that kind of data. So when I have int star star x pointer, it can be one of two things. It is a pointer to an integer, or it can now become a pointer to an array of pointers, each of which points to an array of integers. So it's a two-dimensional array of integers, assuming it's been set up properly. So when we've seen in our main programs where we've been using a list of strings as our input to the program, we've been using this syntax because there's just historical reasons they do it this way, but it's the same thing. It's empty array, that's a pointer, and it's a pointer to that empty array. It is equivalent as car star star argv. It is a pointer to a list of pointers to a set of arrays.
This means we don't need to declare them, right?
Yeah, well, if you have, we're gonna definitely get to that at this rate, probably on Monday. If you know the size of your array, if I know my array is always 22 by 17, then there's not a ton of value in setting up the pointers and doing all that extra kind of coding associated with that. The array syntax is pretty clean. It works for our purposes. We know how to do it. Be done, right? Don't worry about pointers. Where we then have to use pointers is this kind of circumstance, or just in the arbitrary sense, where we don't know at compile or programming time how big those arrays are going to be. And this is the discussion we're going to eventually make our way to of what we call statically allocated memory or statically allocated arrays, where we know it's 12 by 16, versus dynamically allocated arrays, where it's n by m, where we don't know what n and m are until our program has been running for some time. It's based on some variable input to our program. And a lot of the quote-unquote interesting problems we'd want to work on would involve dynamically allocating memory. And so while you can get away with this for a lot of cases, we tend to have to do this when we're dealing with some of those more interesting problems and dealing with dynamically allocated memory. It can also be confusing when you have to do some sort of arithmetic in working with your pointers in C, because you sometimes need to be aware of the size of objects in memory in a way that the array syntax does not require you to. So when you have your array syntax, the code is doing, if I go back to it here, is doing exactly what you hope it would. I want x of I. Well, the compiler is smart enough to recognize, well, x is of this data type that is of a certain size. I want the ith offset into memory, however many bytes that is. It does that math for you. It's effectively this math down here, where it takes the size of the individual element and does that arithmetic for you. But it is oftentimes the case when we're doing some more low-level handling of data structures and the like, that we actually have to do some direct arithmetic on our pointers. We need to change the value of a pointer via some arithmetic or other expression. I think the nice thing, although maybe it's so nice we can trip ourselves up, is that doing math on pointers works exactly how one would hope, that the compiler is also smart in that, in this instance, to recognize that if I have an int pointer versus a car pointer, or any pointers to any two different sized data types, that doing plus plus is going to give me a different result based on the data type that is being pointed to by that pointer. Plus plus, or plus equals 1, whatever you want to do, is going to give me the next pointer, not adding 1 to the value necessarily. So it is explicitly kind of taking the size of the underlying data type into account. Currently, I'm pointing to a certain integer. Now I want int pointer plus plus. That's going to point to whatever the next integer is in memory. It's basically going to add 4 to the raw value of that address. Whereas our cars are just 1 byte at a time, right? So car pointer plus plus gives me just plus 1 to the value of that raw address in memory. I think that's a nice feature. If we forget that that nice feature exists, we can occasionally add too much to our pointers here. So in this setup here, I'm trying to get a little bit more introspection into how things are being laid out in memory. So I put down a couple of integers, a couple of characters, and I set up my pointers to point to car2 and int2 here. Very similar to before. Now we are going to print off our raw pointer. Oh, sure, go ahead, yeah. Yeah, and we'll definitely be getting there. My first suggestion is when you get a runtime error, like the red segmentation fault, and Replit and other environments may say it differently, but that's a very common way. Core dumped, anything of that nature. When you get that error, you step back and say, it's a pointer problem. You may not think it's a pointer problem, but it's a pointer problem. And that helps, I think, at least in terms of it doesn't tell you what line of code it's on, but it should help narrow it down to some extent. Hey, I just wrote this function, it uses pointers. I think it's perfect, but it's crashing now. It's a pointer problem. And then what we'll find that we will wind up doing is we want to kind of start inserting either breakpoints in a debugger or just extra printf statements. The I got this far statement in my program that says, okay, I made it to line 20, but I never made it to line 25. It doesn't always work reliably, but it's a good starting point. Okay, I know I have a pointer problem, and I know it's on lines 21 through 24 or something like that, right, in those lines. That doesn't fix the pointer problem for us, because definitely we then have to go back to our mental model of, I have these pointers. What am I trying to do with those pointers? What am I actually doing with those pointers? The most common cause of crashing a program with pointers, at least early on, is just initializing a pointer wrong, or not initializing a pointer at all. In fact, I set it to 0 explicitly there, but instead, let's just comment out the initialization at all. I have this pointer, it's an int pointer. As part of it, I'm printing out what's being pointed to in memory. By default, that pointer gets initialized to either garbage or potentially to 0 as the address that it's storing. Seems okay. I think we talked about how Replit kind of hides some of what's happening here. It didn't crash, didn't give us the result we wanted. That's going to be a very common circumstance of why something would crash, though. You have an address that's set to 0 or some invalid location, and it's just not. My understanding is that should crash. So Replit is holding our hands here, and maybe it did crash. This new run interface is not very good, right? It did crash, but boy, you can hardly tell, right? If you run it from a more traditional shell, there we go. There's your segmentation fault, core dumped. This is a new feature that just added a couple weeks ago, right? Where you hit the run button, and it didn't finish, and it gives you this tiny little thing that says exit status -1. So some function called return -1, basically, from the shell that we have here. Wasn't that obvious that it crashed, but then you run it manually, and it's pretty clear. Segmentation fault, core dumped. Okay, core dumped. I know there's a pointer problem. I got to line 10, but not to line 11. The problem must be on line 11, I guess, right? That's the only line I have remaining. These are the two things that are following pointers. I'm positive I set these up correctly. Oh, wait, no, it was actually my lab partner. And always blame your lab partner, especially if they're not around. They forgot to initialize that pointer correctly. That's why my code, crashed. They're not always going to be that straightforward and simple, but that has to be kind of the mental process. Thanks for the question, but let's look at the arithmetic of what winds up happening here. 2 integers, 2 characters, and then a pointer to an integer and a pointer to a character we have set up here. We explicitly set up, naming convention notwithstanding, int pointer 1 to point to integer 2, character pointer 1 to point to character 2. We print out the raw pointers. I knew that pointer should be bad. I thought 0 should be bad too, but -1 is definitely bad. We follow int pointer 1 and we follow character pointer 1 to just print out the value. So what should that print out that first time through for following int pointer 1? You have a 50-50 chance. 4. It should print out 4. We've set up int pointer 1 to point to the location of int 2, which is 4. So when I follow int pointer 1, I should print out 4. Likewise, when I follow character pointer 1, I should print out e. 4e, just showing you that. Then I increment them. That's the point of this example here. I'm incrementing the pointers themselves. I'm not incrementing int 2 or character 2, so there's no 5 or f or anything like here. I'm modifying the pointers themselves. Again, pointer is a variable that stores an address in memory, but the data type matters. That's why we have to be very explicit when we declare them, that we have to say it's an int pointer versus a character pointer. Usually, again, we don't print out the raw pointers, but to see what happens here, when I increment int pointer 1, I'm pointing to the next integer in memory. So if the value was 1000, it's now going to be 1004, because it's the next, assuming a 4-byte integer, it's the next integer location in memory. But for car pointer, it's pointing to individual single byte characters. So if the address was 2000, it's now going to be not 2004, but 2001, because it's 1 byte later. I'll print out those raw pointers again to show that the change was by 4 and by 1. And then when I follow them, actually follow those pointers now, unless I screwed it up again, it shouldn't crash. Let's clear that and run it again. That does look awfully crashy. Value equals that, value equals that. What did I change here? Let's initialize them to the other pointers first. I don't know what I did. We will leave things here for today. This example is supposed to show what was the next location in memory. Give me one more try here. Let's print out the raw pointers. Okay. Here's our initial pointers. That's pointer 1 for the integer and the character. Let's call this int pointer 2 and car pointer 2. And let's just explicitly access the address of int 1 and car 1. Let's try this again. Int pointer 1 is pointing to that location. Int pointer 2 is pointing to that location. So when I do int pointer plus plus, the value should correspond to that next location in memory. This is in hex, so it's a little hard to see. And of course, the values can change from run to run. It ends in 0.8, and then after I increment it or go to the next one, it's 0C. That is 4 bytes later. Whereas for the character, it's 0.6, and then gets incremented, and now it's working just fine. Now it gets incremented to 0.7. When I follow int pointer 1, and car pointer is printing out 4E. When I now update that pointer, I've incremented the address, and what happens to be stored in that location in memory is the value of int 1 and character 1. That was the demo I wanted to show, and now it's working. I have a theory as to why it wasn't working a second ago. So this actually does tell us a little bit of something about the compiler and how we declare our variables. What does it tell us about the relationship between int 1 and int 2? Definitely, and I think that's a good thing. They're right next to each other, and yeah, int 2 comes first. That's the other thing I noticed here. We'll talk about this idea of the stack, and that's where the location in memory that things are placed when they're relative to a function. And historically, through convention, stacks grow backwards in memory from high addresses, and that is a very high address, back down to low addresses. I want to see if when I comment out that line again, then it doesn't work again. So this is interesting, right? Code works just fine. I comment out a seemingly unrelated line. I know what happened, but I'm not going to tell you. I comment out what seemed to be a totally unrelated debugging line, and the code does not work anymore. Let's leave things here for today and for the weekend. Good luck as you finish up your Lab 7. We really want to get good with structures, and then we'll talk about how structures and pointers interrelate as well.